Good morning, everyone. Welcome to our final week of our biochemistry weekly reviews and the final week for learning this semester. So this week we're going to do our best to get through all of the electron transport chain, but I also do want to try to keep linking it back to what we've been learning before with glycolysis, with gluconeogenesis, with Tca cycle and everything. So we may not be able to finish it, but I'm going to do my very best. So just because there isn't too much time, I'm going to go ahead and jump right in, okay? So your first few slides are more of a review about the concepts of oxidation and reduction than anything, but they are really important to go over. So one thing that's important to keep in mind is where everything is taking place. So in this case, it's taking place in the inner membrane of the mitochondria, and this is really important for a couple of reasons that we'll see shortly. But one thing I want to point out is there's an enzyme from the Tca cycle that's also in this inner membrane of the mitochondria. And if anyone can remember it, you get bonus points, you get brownie points. But we're going to talk about it in a bit. Just keep that in mind that this is taking place in a specific place for a reason. Okay? And as we see right here, so most of the enzymes in the cycle are in the matrix, which is the matrix is this area right here. It's the very inside of the mitochondria. So when we think of inside and outside, the matrix is what we'd consider to be the real inside. The inner membrane is the membrane between the inside and what's called the intermembrane space, which is exactly as it sounds, the space between the two membranes. And then finally, the outer membrane is between the intermembrane space and the outside. Okay, so most of our enzymes are in the matrix, except for SDH, Succinate Dehydrogenase, because it's along the inner membrane. So this is going to be really important in a little bit, as you'll see, but effectively, SDH is kind of right here, if that makes sense. It's in the membrane, and so so are all of the other enzymes of the electron transport chain. And as an interesting fact, the mitochondria actually has its own DNA and ribosomes, and it does all of its own DNA synthesis. But the enzymes that we use for the Tca cycle for the electron transport chain are actually made in the cytosol. Okay. So jumping into reduction potentials and basically the concepts behind oxidation and reduction, I'm going to start with this formula here. So everything that we've been doing in this class, I've been doing my best to tie back to free energy. I've been doing my best to tie back to why is this going to take place? And this is why the electron transport chain takes place. What's called the standard reduction potential, E0, the change in E0 between the donor and acceptor, and we're going to talk a bit more about that in depth, makes this reaction spontaneous. Okay, so N is the number of electrons being transferred. F is known as the Faraday constant. It's just some value discovered by, I believe his name was Michael Faraday, that I'll show you guys in a bit. And then delta E naught is, well, that's part of the reduction stuff. So effectively, remember, just a quick recap, redox reactions are called that because one molecule is reduced, so it gains electrons. Or I should say, the way that it's drawn here, a reduced donor means something that will be oxidized. So when it's oxidized, it releases these electrons. These electrons have to be picked up by something, and they end up being picked up by the acceptor. Okay, redox is always redox. There's no such thing as just a reduction reaction and just an oxidation reaction. They always come in that pair. Okay, so delta E naught is the standard reduction potential of the acceptor minus the standard reduction potential of the donor. And we're going to see this in a graph in a little bit just to show it. But if delta E is positive, then, oh, the formula's right here, I forgot. So if this is positive, well, the Faraday constant is positive, and N is just some number of electrons, so that's got to be positive too, meaning that this overall value will be negative because of this thing, meaning spontaneous, right? So, and as it says in this last bullet point, the redox couple, when it says couple, it means, for example, NAD plus to NADH, this is one redox couple. We don't want to say NAD plus because it's not always going to be in the form of NAD plus. So we say the redox couple of NAD plus and NADH. And it's really important that we do that because, for example, iron can go to iron 2 plus or iron 3 plus. And so it's important that we have the specific couple in mind, not just a single molecule. So anyway, so the redox couple with the more negative reduction potential will donate the electrons. Okay, so let's think about what that means. So we'll donate electrons. In other words, it'll be the donor couple. And that's the more negative reduction potential. So the smaller one, right? So this number, so if we call these X and Y, based on what this is saying, one is more negative, one is more positive, that means X is greater than Y. In other words, because spontaneity is what drives a reaction, the spontaneous reaction is the reaction in which X, and I just realized this Y does not look like a Y, in which X is greater than Y. And this works because you can have one molecule reduce the other, or that initial molecule reduce the first. And so it can kind of go both ways, and that's why we're very careful about it. So this is a great example of ethanol being converted into acetaldehyde, and this is also a great example of what's called a voltaic cell or a galvanic cell. So standard reduction potential is measured in the reaction half cell. The sample half cell contains 1 molar solutions of the reduced and oxidized form of the species being measured. Okay, so let's talk about this in depth. So your reference is hydrogen, and the reason that we see that is because if you look at the table of standard reduction potentials, this reduction from H plus to H2, its E naught is equal to 0. 0 joules, 0 volts, 0 volts. And so the reasoning here is if we define this to be 0, the difference between this and, in this case, ethanol to acetaldehyde is, we're just going to say, is the reduction potential of ethanol to acetaldehyde. And so we can expand this to mean to all of them because we don't care that, if H plus to H2 is actually 10 volts, we only care about the difference between H plus and H2 and ethanol to acetaldehyde. And that's why it doesn't matter that we defined 0 to be H plus to H2. It's fine being that. So let's look at this thing. So the electrons are able to flow through this voltmeter, or potentiometer in this case. And when these electrons flow, ethanol in this solid is released into solution as acetaldehyde. Okay, so yeah, okay. This is all things that I've been saying. Okay. This is the reaction of ethanol to acetaldehyde. It releases 2 protons and 2 H2 gas. Or I'm sorry, 2 protons and 2 electrons, excuse me. And if you notice, those 2 protons and those 2 electrons are what are used on the reference cell, or in this case, the right side. And so when we add the 2 reactions together, this is what the bottom overall reaction is what we're left with. So as mentioned, standard reduction potentials are measured at 1 molar concentrations, 1 atmosphere. So as it says here, since the pH in the reference cell is 0, or I should say that makes the pH in the reference cell 0. Excuse me. So, as we remember from the basic ideas of delta G naught and delta G naught prime, it comes up once again. So because in biochemistry, we care about pH 7, or about pH 7, we use E, or I should say it's really epsilon. I keep saying E for convenience, epsilon not prime. And so that's why, according to most tables, you'll see the reduction potential of H plus to H2 being negative 0.42 instead of 0, and so because of that pH difference. And this is giving you a bit more of the information. So, so the remember that it's acceptor minus donor. In this case, the acceptor is the hydrogen, and the hydrogen is accepting 2 electrons. Oh, they'll do that. Okay, they do that later. So the hydrogen is accepting 2 electrons, and its standard reduction potential is 0. The reason we subtract is because we're subtracting reduction, and this is oxidation. So we're basically taking the negative of it so we can flip it into oxidation. And so that's why this value is here. They get subtracted from each other, and this gives us this. And if we were doing this, although this is a general chemistry topic more so than a biochemistry topic, we could plug in that NF epsilon naught, or I should say delta epsilon naught, and get this delta G value. Okay. All right. So in this case, we have fumarate to succinate, and this one tells us that the standard reduction potential of this one is positive. In other words, whereas this one was negative and went from reduced to oxidized, this one is positive, so it's going to go from oxidized to reduced. Exactly, so it'll reduce fumarate to succinate. So here is the table of standard half reactions. It's always written in the form of the reduction. So positive reduction potential means that I don't like this lingo, to be honest. It kind of confuses me. A positive delta E naught prime of a half reaction tells us that this reaction wants to happen. A negative one, like for example this one, means that the reverse reaction is more likely to happen, and this is more likely to be oxidized. Okay, so the higher up on this table you go, better at being reduced. Okay, so if we notice here the transfer of electrons from NADH to O2, I keep trying to say OH, I apologize, is what drives biological energy. And here's why. NADH and NADPH both have reduction potentials of negative 0.32. Oxygen has a reduction potential of 0.8. So when we do this, to calculate our delta E naught, our delta epsilon naught, I should say actually this is prime, we're going to take the standard reduction potential of the acceptor, which is oxygen, 816, and subtract that from the reduction potential of the donor, which is in this case a negative number. So we add them up. We're going to get a value that's pretty large and positive. When multiplied by Faraday's constant, this ends up equating to a really, really spontaneous reaction. So here's one great example from your that your professors have done with the Tca cycle. So this is the reaction of isocitrate to alpha ketoglutarate, and they've split it up into its 2 half reactions. So this is the oxidation reaction, and this is the reduction reaction. Okay, and if you notice, oh, and I should mention this is the reduction this is the reduction that ends up being flipped, right? It's important to keep in mind. And the reason is this one is more negative. We want to get the most positive value possible. So in other words, we need delta epsilon naught prime to be greater than 0 for delta G naught prime to be less than 0. So if we want it to be spontaneous, we need this number to be positive. The only way to do that is if we flip this one and then add them together. Or in other words, make this the donor. Okay? Or I'm sorry, make this the acceptor. Yes. So, as it says here, the one with the more negative one donates electrons to the less negative or the more positive. So isocitrate is a better reducing agent than NADH and releases the electrons more easily. And so as we see here, your donor, acceptor, and then in this case, it actually gives you the Faraday constant, which is 96.5 kilojoules per volt per mole. When you multiply these together and you find out that you have the release of 2 electrons, you get this very, very exergonic reaction based on the electrochemistry. Okay, and obviously it's not quite right, simply because we're not always dealing with 1 molar concentrations, with the exception of that H+. And so this is a variation of this formula that gives us epsilon rather than epsilon naught. Okay. All right. So now we can kind of start jumping into the Tca cycle, or I'm sorry, the electron transport chain. Before we do, I told you guys very briefly that the reaction from NADH to oxygen, that transfer of electrons, is very, very spontaneous. Here, your professor is quantifying it for you and telling you it's negative 219 kilojoules per mole. Incredibly spontaneous, and this is what serves as the energy to make ATP. Okay. So before we jump into the actual, here's what's going to this, then to this, then to this, we need to start talking about a couple of intermediates that we use. So CoQ, coenzyme Q, Q, ubiquinone, all of these are variations of the same thing that we can call, it. It's one of our mobile electron carriers in the electron transport chain. So if you notice, it's hydrophobic because of this long tail, which lets it stay in the membrane and lets it be transferred and lets it kind of move through the membrane. Okay. So this thing in its oxidized form can accept 1 electron to go to what's called a semiquinone intermediate, and then it can also accept a 2nd electron to go into what's called ubiquinol, or its reduced form. So it goes ubiquinone to ubiquinol with 2 electrons and 2 protons. Okay. So we use iron sulfur clusters. I told you they wouldn't. I told you that they weren't going away. So let's look at this as an example. So we have NAD plus and we have O2. NAD plus wants to transfer its electrons to O2. So how does it do that? Here's the reactions. NAD, they keep flipping these and it hurts my head, I apologize. So NAD plus is going to release 1 hydrogen, 2 electrons, or I should say 1 proton and 2 electrons. Ubiquinone, or I believe actually ubiquinone is going to accept those and be converted to ubiquinol. Ubiquinol is then going to release those and give them to the oxygen. Okay, so NADH transfers its electrons to here. Get picked up by ubiquinone, which is converted to ubiquinol, which transfers them to here, which gives them to the oxygen. Okay, and that allows for proton pumping because of what these specific proteins are. So this NADH dehydrogenase and this quinol oxidase, we're going to be talking a little bit, well, I should say a lot more about kind of the mechanism of action with the iron sulfur clusters that allows these protons to be transferred and the electrons to be transferred to the ubiquinone, and then from the ubiquinone to the ubiquinol. Okay, so here is the basic overview of the the electron transport chain. So over here on the far left, NADH is converted to NAD+. Okay, so it is reoxidized. So remember that the point of lactate dehydrogenase was to go from to use up our NADH so that we could get more NAD+ for more glycolysis. Well, the electron transport chain has that as a goal as well. Okay, so in addition to making ATP, it also regenerates our NAD+ for future glycolysis. That's the first thing it does. The second thing it does is it pumps 4 protons this way. Okay. The third thing it does is, I believe it's 2 electrons to convert ubiquinone to ubiquinol, and then that ubiquinol can transport it from, and this is complex 1 by the way, to complex 3. Complex 3 then transfers them using this Cytochrome C, which we're going to talk about again in more depth, into complex 4. Now I'm going to pause before we get into complex 4 because we have to do something with complex 2. So complex 2 is succinate dehydrogenase. We learned about this in Tca cycle. We're going to learn a bit more about the mechanism and everything, but it's really important to note that this converts FADH2 into FAD. And in doing so, it transports it once again using that ubiquinol mechanism into complex 3. Complex 3 then sends it to complex 4 with the cytochrome C. Okay, then complex 4 is where Your O2 is converted to O8, or to convert it to water, excuse me, and in doing so, we pump another 4 protons. And I forgot to mention the proton pumping in complex 3. I apologize, we will get to there, I promise. So in other words, we're using 4 complexes, 3 of which pump things, and 1 is a part of the Tca cycle. We're using 2 mobile electron carriers. One is the ubiquinone-ubiquinol, and 1 is Cytochrome C. So let's talk about this in more depth. So this is everything that I was saying. Okay, actually there is one further purpose, right? And that is the proton pumping. I kind of very briefly said it pumps protons to the other side. I never said the importance. So the importance is this proton gradient that's discussed at the bottom. When you have a gradient like this across a membrane, it gives us energy. So as the protons transport back this way, that's how we make ATP. And you're going to see that later. I just want to make sure to mention it now because everything has a purpose here. Okay? So here is complex 1, what we're actually dealing with. So complex 1 is called NADH dehydrogenase because that's the easy way to call it, or that's the easy name for it. More specifically, it's called NADH coenzyme Q reductase. Why? Because NADH is one of its substrates, coenzyme Q is its other. If you want to think of it in terms of substrates, this thing is huge. It's got 1 flavin mononucleotide, it's got 9 iron sulfur clusters, 43 polypeptides. Okay? So the first reaction that occurs is 2 electrons are released from NADH and they're used to reduce FMN. So our flavin mononucleotide is reduced to FMNH2. Then, actually I think, yes, it goes into more depth in the next slide. Okay. So it's important to recognize that this is just a model. And the reason that this is important that I say that is because there's no iron sulfur clusters up at the top. They're all in this part down here, all 9 of them. Okay? And the second reason that it's important to recognize this is just a diagram is it makes it kind of seem like your coenzyme Q is inside this complex. It is not. Okay? All right. So this is a bit of a better diagram. So it shows here, like that first reaction is FMN. Then you have your series of iron sulfur clusters that help you transfer the electrons into coenzyme Q, which is then reduced and sent on its way to complex 3. Okay. So I want to point out we have 2 protons that were introduced here, and then 2 protons that were introduced here for a total of 4 protons pumped. This is something that confused me a lot when I first learned this because I saw 2 protons over here and then 4 protons over here, and I was like, where are the other 2 coming from? The other 2 are coming from this step. Okay, the reduction of ubiquinone to ubiquinol needs 2 needs 2 protons as well. Okay, so that's kind of the gist of complex 1's reactions, or I should say transfers, because these are all electron transfers. We talk a bit about the energy behind it, and all it's telling you is the standard reduction potential of FMN is more positive. In other words, it's more likely to be reduced. In other words, the reduction can occur and electrons will flow from NADH to FMN. Okay? The true reduction potential is affected by the environment, and so it's not quite as spontaneous as it seems here. Okay? So we're not certain exactly how this goes, admittedly. Science is hard, obviously, but what we do know is that this chain of iron sulfur clusters is not completely identical. So this one is different from this one, which is different from this one, and so on, because each has a more positive reduction potential than the last. And so if we think about this in terms of energy, the electron transfers all want to occur because they're all spontaneous. Okay, that's an important thing to note. Now this is a little bit about the structure. You've got your membrane domains, which are 7 subunit and 54 transmembrane helices, and then you've got 8 in the hydrophilic region, or in the hydrophilic domain, which is the mitochondrial matrix. Okay? And here's the kind of the map of the iron sulfur clusters and the FMN and everything. And the paraplasm. So what's the error? So it's right here. This is the cytoplasm. This is the intermembrane space. These two need to be flipped, okay? Because complex 1, this globular region is in the cytoplasm, okay? All right, so we talked about coenzyme Q. Yes, okay. Right, so now kind of going backwards, UQH2 or QH2 ubiquinol over here releases 2 electrons and 2 protons. When it's converted back into ubiquinone. And this occurs at complex 3, and we're going to talk about that when we get to complex 3. Okay? And that's, oh, and then yes, the semiquinone intermediate is important in complex 3. Okay? Okay, yeah, so like I said, you have 2 protons here. 2 protons here. These guys are important. You can't just ignore them. I ignored them and I didn't get it. Okay. And finally, yeah. Okay, yes, this is just talking about more of the proton pump. Okay, so like we said, the iron sulfur clusters are different, and they differ by effectively 1 unit and can do 1 electron redox reactions. FMN can do 1 electron reactions, but it can do a series of them, or it can do 2 electron reductions. And that's why it's able to accept 2 electrons from NADH and then do single electron reactions with the iron sulfur clusters, because it can do both. Okay, and here's another kind of form of reaction pathway. If this helps you, that's great. Like, use whatever's best for you. I don't personally like these as much, admittedly. So I'm going to go ahead and skip until here we go. So back to here. Complex. Okay, yes. So this is the talk about complex 2 now. So succinate dehydrogenase, FADH and FAD are not on the outside like this, like they were for complex 1. Okay. Ooh, excuse me. I don't know why it just dropped me all the way back there, but I can kind of point it out here now. So in this one, we saw NADH to NAD plus on the outside. That doesn't occur on complex 2. Complex 2 has it localized within. Okay, so it's a covalently bound flatland right here. And then it's got 3 iron sulfur clusters, these 3, and 1 heme group. Okay? All right, so let's talk about it. So this thing, iron protoporphor 9, it's found in cytochrome B, it's found in myoglobin, it's found in hemoglobin. It is, what's the word that I'm looking for? It's a really helpful resource for your body because it allows it to participate in redox reactions more. Okay, we're not going to talk a ton about this because, I mean, you guys have learned hemoglobin, you know there's a lot going on there, and I don't really want to take the time to unpack all of that. But, so heme is on the electron transport route. We thought. It's not. So there are no protons transferred across complex 2 into the intermembrane space. Okay, that's important to keep in mind. So generally speaking, we believe that the order is FAD through the 3 iron sulfur clusters into heme B. And then, as we mentioned, unfortunately, okay, there we go. Heme B transfers its electrons to ubiquinone to convert it, I'm sorry, do I have that backwards? I apologize. To ubiquinone. Ubiquinone is then converted to ubiquinol. This arrow is backwards. Ubiquinol transports those electrons into complex 3 and is converted back to ubiquinone. There we go. Okay, and I apologize, this is not the most beautiful diagram. Okay, so, right. So there's this thing called the Q cycle. And effectively, the Q cycle is how we go from ubiquinone to ubiquinol back to ubiquinone over and over again without, having that weird kind of unbalanced thing where we don't have enough of one, too much of the other. So we're going to start with ubiquinol, which is the the UQH2. It bounds to what's called the QP site of, in this case, of some enzyme. In this case, I believe this is complex 4, or I'm sorry, complex 3. That UQH2 goes into its semiquinone form and then into its ubiquinone form. And in doing so, it releases 2 electrons. The first electron is transported eventually to cytochrome C. Okay. The second electron is transported through 2 cytochrome Bs, and we're going to talk about them later, into UQ. And this UQ is on the outside. It binds to the QN site and is converted to UQ minus. So you regenerate this UQ, I should say. So this is the original UQH2, and it goes to a UQ minus. So why is that important for us? But this is the next half of the cycle. So now, a second molecule of UQH2 goes to the P site. The same reactions happen. So now we've given 2 electrons to cytochrome C, and we've transferred now 4 protons, because we transferred 2 in the first step and 2 in the second. And I forgot to mention them in the first step, I apologize. And now this UQ is regenerated, or I'm sorry, it's converted back into UQ, and we're happy with that. The second electron once again goes through 2 cytochrome Bs, and it helps convert our semiquinone back into a ubiquinol fully. Okay? So how does this help us? This is what allows the proton pumping to occur, and it gives us 4 protons being transferred. And if you notice, only 2 of them are coming from the mitochondrial matrix. The other 2 protons are coming from, what's it called? I apologize. From our semiquinone, or I'm sorry, not from our semiquinone, from our ubiquinol. From UQH2, those 2 H's are released. And the same thing is happening here, but we're also using 2 protons to make more of UQH2, okay? And so this helps us release protons into the intermembrane space, which you'll see is kind of the most important, or I shouldn't say the most important, one of the most important things that this process does, okay? And this is a lot of the subunits that is very complex. Okay, so now cytochrome C. This is just something to point out. Every student should be very familiar with complex 3. It is very, very important, okay? So now cytochrome C, as we've been talking about, is this thing that kind of moves electrons around in the intermembrane space. So it's oxidized, and then it's reduced, and then it's oxidized, and it's reduced, and repeat. So complex 4 is called cytochrome oxidase. So let's think about why this is. Because it's pretty straightforward. It's oxidizing cytochrome C. The names themselves are pretty simple. It's just we try to make it more complex for ourselves. So in order to oxidize cytochrome C, it needs to reduce something, right? Redox reactions always come in those pairs. What does it reduce? It reduces oxygen into water. So this is the overall reaction that takes place, but there's one thing that's really interesting to note here. The first is that, I apologize, I lost my train of thought. So the first is that your cytochrome C is on the intermembrane space side, and your oxygen is on the mitochondrial matrix side of the membrane. In other words, they're on different sides. So it's not that these two are reacting with each other directly, and that's why there's this concept of a terminal acceptor and a terminal enzyme. So oxygen is the terminal electron receptor, or I'm sorry, acceptor. In other words, all these electrons have flowed from various regions, and they're eventually going to make their way to oxygen. Complex 4 is the terminal oxidoreductase. It is the last enzyme in this oxidation reduction chain. So let's talk about that mechanism again. So important to keep in mind, you have one cytochrome C transporting 1 electron, right? This this oxidation is from 2+ to 3+, so only 1 electron is being released, okay? So we, rather than try to make a cytochrome C that transports 2 or 3 electrons, we just use 2 cytochrome Cs. And so we have each cytochrome C releases an electron. And now rather than dealing with iron sulfur clusters, which which I don't believe that complex 4 has, we have 2 copper centers. So copper center A and B, which I believe they're pretty similar, but we just do that for notation. They each accept 2 electrons and release 2 electrons into cytochrome A, and then into cytochrome A3 and copper B, which are linked, and then into water eventually. And in doing so, it pushes 2 protons this way. Okay. So, yes, so this is all the cytochrome A to cytochrome A3 copper B. Okay, so this is the same thing. Let's go into a little bit more depth. Actually, I think that's as much depth as they go into. So this next idea, this next concept is the idea that we could be dealing with something bigger than just 1 or 2 complexes, and that's why they call this maybe a super complex. Oh, this is, I'm sorry, I love this graph. I forgot this was in this chapter. This is a graph of epsilon, our standard reduction potentials. And if you notice, we start with NADH, and then, or I should say, yeah, NAD plus NADH. FMN is at about the same level. While you do have to go the other way a little bit, generally speaking, your iron sulfur clusters are going this way, and then they're able to transfer to UQ. UQ is able to transfer it to complex 3, excuse me, and then all the way down this line. It's a little bit less straightforward with complex 2, but effectively it does the same thing. Okay, there is a fairly downward path that it basically makes it to where all of these reactions are pretty spontaneous or are driven by a spontaneous reaction. So for example, when we talked about the reaction of oxyl acetate and acetyl-CoA in the Tca cycle, we said it's not very spontaneous, and it's actually kind of not very, it's not a very good reaction, but it's driven forward by how spontaneous the citrate to isocitrate reaction was, or something like that. And so it's really important to keep that in mind. So Peter Mitchell had come up with what's called the Chemi Osmotic hypothesis, and it says the potential energy associated with the proton gradient across the inner mitochondrial membrane provides the driving force for the synthesis of ATP. So those are a lot of words. So let's break this down. Potential energy associated with the proton gradient. That's one thing. So this is the energy, and actually, really, it's across the mitochondrial membrane. This entire thing is the energy. So this is the driving force for the synthesis of ATP. In other words, what's providing the energy? This thing in this location. Okay, so let's talk about it. So I've been telling you guys we're going to pump a bunch of protons into the mitochondrial membrane. Or I'm sorry, into the intermembrane space. Ton of protons. So now this proton pump, or I'm sorry, this makes the intermembrane space, as you guys can see from this part right here, pretty positive relative to the, or I should say, and this relatively negative on the matrix. So what does this do for us? It makes, and you guys can see this F0 and F1. We're going to talk about this in a lot more depth, but this is ATP synthase. It allows protons to travel through here, and in doing so, spin ATP synthase to create ATP. Okay, and again, we're going to talk about the mechanism in a little bit, but the reason that I point this out is because we're reusing all the protons that we sent through to make ATP. So what we see here is this new formula that's kind of similar but kind of different. So let's kind of dissect all this. So yes, we're sending protons across the membrane. Awesome. The stoichiometry, we're not 100% certain, but this is what we estimate. So per molecule of NADH, it seems like we send about 10 protons through the membrane. And this, let me see if I can find a good picture of our what's it called? Okay, so here. So NADH sends 4 from complex 1, and then it's transported to complex 3, which sends another 4, and then to complex 4, which transfers another 2. So that's where the 10 from NADH comes from, whereas succinate to fumarate does not go through complex 1, but it goes through complexes 3 and 4, and so it only has 6. Okay, so that's where that's coming from. That's why those are the generally accepted values, because they seem to make the most sense based on what we know of it. So now the free energy associated with this movement has two components. There's the concentration gradient, and then there's the electrical potential. So let's talk about each of these in order. So the potential difference is there's an electrical potential. Electricity follows the same basic concept as everything else. We don't like to be on a hill, so we're going to roll down that hill. Same thing here. There's a potential difference. We want to roll down the hill till everything is the same. Okay? And the proton gradient with respect to concentration follows the same thing. And this is this equation. The first one comes from negative RT ln except they've converted this. So now this is log H plus out minus log H plus in. And as you know, with logs, you can write that as a fraction. And then this term right here is the conversion from natural log to log. Okay? So that's where that's coming from. The potential difference is pretty similar to what we just learned with Faraday. It's got Faraday's constant, and then rather than using an epsilon, we're using what's called psi. Okay? So the membrane potential is plus 18 volts. The difference between the pH of the external and the pH of the internal, or I should say of the out, which is the intermembrane space, and the pH of the mitochondrial matrix, is about -1, it's estimated. And so at 37 degrees Celsius, about internal body temperature, we get 23, we get 23.3 kilojoules. Okay. In other words, this is the movement from inside to outside. Okay, so this is a movement of more electrons into the mitochondrial matrix. Or, I'm sorry, into the intermembrane space, where it's already really, really positive. Okay. On the other hand, if we move down that concentration gradient from the intermembrane space into the mitochondrial matrix, it's very, very exergonic, negative 23.3 kilojoules. That's very spontaneous. That really wants to happen, and we can use this energy to drive other reactions. Okay, and this is kind of similar concept to water. It's it flows downhill through the turbines to produce electricity, and then it's pumped uphill. Okay, so how does the proton gradient drive ATP synthesis? Great question. So we talked about F1 and F0 very briefly. So F0, I'm going to start with because it's a little bit easier. It's got it's got A, B, and C subunits. And it forms the pore through which the protons move. So in other words, it's a transport channel that that protons can flow through. F1 is basically the synthase, and it's got an alpha. I'm sorry, do I have this backwards? No, I'm sorry, it's alpha 3, beta 3. So 3 alpha subunits, 3 beta subunits, and then 1 gamma, 1 delta, 1 epsilon. Okay? So the 3 alpha and the 3 beta are kind of like they make this 6. I think of it as a wheel. I don't know if there's a formal term for it, but in my mind, it's a wheel. So then the gamma and the C subunits, and you can't really, yes, you can, there we go. So the C subunit is here at the bottom. So this is the C subunit by the way of the F0 component, and then the gamma subunit of the F1 component rotate together with respect to the A and the B. In other words, we have rotation, and that's what's causing this, that's where the energy is going, effectively. And I do want to point out, yes, we do have those delta and epsilon. We're going to talk about those later. Okay? So the A and B are the stator, or they're stationary. The C and gamma are the rotor. They move. Okay? All right. So this is the A subunit. Okay? So protons taken up, well, I should say really this is the F0. But within the A subunit, a proton is taken up from the intermembrane space through this channel. And it's transferred specifically through an aspartate residue. Where is it transferred? To the alpha helix of the C subunit. Okay, so that's what we see here. This makes the C subunit rotate. Okay, so why does it rotate? It rotates in order to allow this proton to be released into the matrix. Okay, so we talked about how this rotation is kind of a conformational change and how that conformational change can allow for further reactions to happen when we talked about the MWC and the KNF models. This is a fairly similar thing happening here. Okay, and this is kind of what it looks like if we're looking kind of from a bird's eye view of what's happening. So a proton is accepted into the aspartate of one of our C subunits, and it's transferred to another opening. Okay, and then that makes this this aspartate now negatively charged because the proton is here. This negatively charged thing is going to move closer to the positively charged arginine, and that's going to actually allow another proton to be transported from this arginine to the aspartate. Okay, that's what we see here. That causes now this rotation of, this rotation of that C subunit further away. I apologize, I'm on the wrong carbon, or I'm on the wrong C subunit. But effectively what we see is it coordinates together to transport this proton into the S subunit. Okay? Yeah, it's a bit complex. Let me try to re-explain that because I think that I explained it poorly. So I'm actually gonna just clear everything that I drew here because I think that I got a little bit confused, and I apologize for that. So for convenience, I'm gonna say C1, C2, and C3. So at the moment, the A subunit's arginine is helping to stabilize C2 and C3, which are both negatively charged. But that C2 subunit, that C3 subunit is going to take one of the protons from that arginine, and in doing so, it's going to be able to get further away since it no longer needs to be stabilized by the arginine. And when that happens, C1 can get closer, and C2 can kind of shift over to the, in this case, to the right. And so now we can see that C3 is out of the way. C1 and C2 are both close to this A subunit, and this allows the transfer of this proton to the serine residue on the A subunit. Okay? So now the A subunit is the positively charged one. So if we look up here, it's the C subunit and the A subunit it's the arginine that's positively charged here, still the arginine, but the aspartate, if you notice, did they not draw the charge? They should have drawn the charge on the aspartate. I apologize. Okay, never mind. So that effectively drives the rotation. So that's what's happening that's causing the C to rotate. One of them is losing its charge, the other one's gaining a charge, and moves the C, the rotor, if you will, parts of the subunit. And then that moves the gamma subunit. And the rotation of the gamma subunit drives the conformational changes in the alpha and beta subunits, which provide the energy. So this is kind of similar to the MWC model. It reminds me personally of the MWC. We're going to kind of think about this with a similar perspective, but knowing that it's different. So you have this loose subunit, which is inactive and has what's called a loose affinity. Okay? We have our tight subunit, which is active and has a high affinity. So this is the one that's reacting. And then finally, the open one is inactive with a low affinity. Okay? We need one complete rotation of the rotor to synthesize 3 molecules of ATP. Okay? Why? I'll get there. So I'm going to, I apologize. I did not mean to draw the line. I meant to zoom in closer. So we have a tight, a loose, and an open. So the tight subunit is going to bind to an ATP. Okay? When it does that, actually, oh, they draw this backwards, don't they? No, they draw this the right way. Okay, so it binds to an ATP. And now if you notice, the loose subunit, or the L subunit, picks up an ADP. Okay? And in doing so, we now have a conformational change. So this with some energy, now rather than this top one being the loose one and this one being the tight one and this one being the open one, this becomes the new tight one, this becomes the new loose, and this becomes the new open. Well, the open subunit has a very low affinity for ATP, so this thing's going to leave, and through ATP synthesis, the tight subunit is going to react to convert the ADP that it had into an ATP, and once again, we get a conformational change and repeat. In other words, what we're seeing here is each subunit is going through this cycle from loose to tight to open, from loose to tight to open, and repeat. And in doing so, when it becomes the tight subunit, it can react with ATP. And then when it becomes the open subunit, it can release that ATP. And then the loose subunit is kind of the intermediate, okay? This is another way to look at ATP synthase that I think is also pretty indicative. So this one actually shows gamma and epsilon a little bit more, and the B subunit of the F0, okay? Yeah, a little bit more information there, a little bit more. They like to give you guys a ton of drawings just because it can be really helpful to see in different perspectives. I personally stick to the ones that I like the most, but I encourage you, if you find one that you like, use it. Do not take my kind of indifference to it as a negative sign. It's just I found ones that were better for me. Yeah, okay. So the membrane potential across the inner mitochondrial membrane drives the export of ATP and the import of ADP by ATP-ADP translocase, and this process diminishes the proton gradient by the equivalent of 1 proton per ATP. That's a lot of words. What it's telling you is the ATP has a ton of, or I'm sorry, the matrix has a ton of ATP once ATP synthase works, right? So what if the cytosol needs some? Or I should say the cytosol, yes, so the cytosol can now transport it in to exchange it for ADP. And what that does is effectively it exports ATP and imports ADP so that you can make more in the matrix, okay? But that takes energy. So what we see here, this arrow, is how much energy that takes. Per 1 ATP out and 1 ADP in, we lose the equivalence of 1 proton in. And so that starts to diminish the proton gradient a little bit. So yes, we talk about 10 protons and 6 protons per NADH and per fumarate. And I want to talk about this in a little bit more depth in a moment, but not all 10 of those protons, for example, are going to ATP. Some of them are going for this transfer reaction so that we can get the ATP out of the matrix and into the rest of the body that needs it, okay? All right, so 10 ATP are translocated for each NADH oxidized. So we talked about this briefly. 4 in complex 1, 4 in complex 3, 2 in complex 4, okay? All right, so the P to 0 ratio, and this is one that really confuses me half the time, so we're gonna go with this one slowly. It's one of those that makes sense when it does and doesn't make sense when it doesn't. So the P to 0, I'm sorry, not the P to 0, the P to O. I abbreviated P to 0 for some reason. So the P to O ratio is the number of ATP molecules per 2 electrons that enter electron transport. So 2 electrons is effectively oxygen, right? It's how many electrons you need to go from that 1/2 O2 plus 2 electrons plus 2 protons into H2O, okay? That's why it's called O, even though it's per 2 electrons. P is phosphate, if you want to think of it like that. One phosphate group is transferred to ADP to make ATP. So, as we've said, 10 protons and we transport 2 electrons. 12 protons drive 1 complete turn of the enzyme, which generates 3 molecules of ATP. Okay, so the H plus to ATP ratio is 12 to 3, which is 4. In other words, 1 ATP is made per 4 protons. And we know that we have 10 protons here, right? So if 1 ATP is made per 4 protons, then 10 over 4, because we have 10 protons from NADH, is 2.5. And that's 2.5 per 2 electrons, which makes 2.5 the P to O ratio. Okay, and that's disregarding the cost of ATP transport out of the mitochondria and everything like that. Okay, so in the mitochondria, one proton is consumed in the export of each ATP molecule. So now it doesn't just take 4 protons to make 1 ATP, it takes 5, okay? So now it's not 10 over 4, it's 10 over 5, which means 2. So 2.5 is an acceptable answer for the P to O ratio. 2 is the more complete answer because it accounts for the cost of transport, or export in this case, all right? So now, this is a pretty confusing part in my opinion. When you have 10 C subunits, 8 C subunits, 12 C subunits, whatever the case may be. So the reason that we need 12 protons to drive 1 complete turn is because we have 12 C subunits. And these 12 C subunits, you have to protonate each and then release that proton for every single subunit in order to have 1 complete turn. And because we have 12, that 1 complete turn generates 3. On the other hand, if you had 10 C subunits, then it would take only 10 protons to drive 1 complete turn, which would still generate 3 molecules of ATP. I apologize. And so in this case, you would get an H plus to ATP ratio of 3.33. 3.33 ATP molecules are made per, I'm sorry, hang on. I keep going backwards. Per 2 electrons, you make 3.33 ATP molecules. There we go. And so your overall ratio with only 10 subunits would be 2.31. And with 8 subunits would be 2.7. We make 2. So this is just kind of an indication that if we had different numbers of subunits, we could get more energy out of that ATP. Okay. So we talked about Mitchell's chemi-osmotic hypothesis, right? And I'd like to go back to that to make sure that we know exactly what it says. It's the thing that states that the potential energy from the proton gradient between the intermembrane space and the mitochondrial matrix is the driving force behind ATP. Okay, so let's erase this so that we can read this again because I kind of drew all over it. The potential energy associated with the proton gradient across the inner mitochondrial membrane provides the driving force for the synthesis of ATP. So jumping back down, so this is called the Racker-Stokenius experiment, excuse me. Guess who came up with it? Racker and Stokenius. And it confirmed Mitchell's hypothesis. So what we're looking at here on this left is called bacteriorhodopsin. And it's a light-driven proton pump. And finally, ATP synthase on the bottom. So they were reconstituted into this lipid vesicle. The reason they did this is to basically control exactly what was coming in and going out. So this way they know the only things that are doing anything to affect protons are this bacteriorhodopsin, which allows protons in with light, and ATP releases protons to make ATP are present. So, needless to say, ATP was synthesized in response to light. Not too complex, right? And so this verifies for us that it is the protons moving down their gradient that makes ATP. So this confirms Mitchell's chemi-osmotic hypothesis. And it's part of the reason he got a Nobel Prize, because he was right. Okay, so we've talked about this process in terms of what we want to see happen. We've talked about this process in terms of this is the ideal, this is what's going to drive it forward, what's going to keep it going. Guess what? Things can ruin it, and they're called uncouplers. So effectively, they increase what's called the proton conductance of the membrane to collapse the proton gradient. So you see how, well, first let's talk about the fact complex 1, complex 3, and complex 4 are the things that contribute protons, or I should say that pump protons. And then those protons are taken to ATP synthase. So that's 4 locations that can screw everything up, and technically a 5th. So complex 1, these 3 proton uncouplers can ruin its proton pumping. Complex 4 has these guys. Complex 3 doesn't have any, funnily enough. And ATP synthase has oligomycin. And then finally, another way that things could be ruined is if we had another way to get protons out that didn't involve ATP synthase. Okay, sorry, I don't know what happened. My OneNote froze for a second. Just wanted to make sure everything's working. So these three are uncouplers that will just send everything straight through. Okay, so here's a great example. So DNP is dinitrophenol. Just want to make sure that I emphasize that. So the charged species of DNP can cross the membrane because of the charge delocalization, which makes it semi-hydrophobic. I don't want to call it hydrophobic, it's not, but for the purposes of the membrane sees it as being kind of hydrophobic because it's not very charged because of all this resonance that can occur. And then it can take on a proton and leave, and that's why it's kind of uncoupling. Okay, so the mitochondrial proton circuit is analogous to an electrical circuit. This is something that I think is really fascinating. Effectively, what we see here is, so this is a battery. What they're calling a battery is the electron flow into oxygen, and then protons flow. In this case, electrons are the quote-unquote protons here. They flow to the ATP synthase, which is what we're trying to power, which gives us the light bulb. So the potential difference, the electron transport chain, so yeah, versus a battery. Current is protons versus electrons. So in this case, the protons are what provide the power through the proton motive force, and effectively we get ATP synthesis, whereas an electrical circuit would give us light and heat. Okay, so an uncoupler is effectively a short circuit. It cuts out ATP synthase and just gets the and it stops the work from being done and dissipates the energy. So that's why these three, DNP as it calls it, or dinitrophenol, dicumarol, I apologize, I can never pronounce that, and FCCP, these guys make it to where all this work that our four complexes do is for nothing because they circumvent ATP synthase. Okay. And this is a great example. The short circuit is introduced, no light is on. Okay. All right. So natural uncouplers provide a source of heat, right? It makes sense because the energy has to be dissipated. Somehow it gets dissipated by heat. Okay. And the final slide of your PowerPoint and of really this entire class is we use what's called brown adipose tissue for this purpose. Okay. So the absorbed fats and sugars provide energy for our daily functions, and then obviously the excess is stored as fat in white adipose tissue. Okay, brown adipose tissue is activated in response to various stimuli, such as exposure to cold, and it burns fats and sugars to keep us warm. Okay, and the reason that you see this figure of both a male and a female is because the process seems to be more prominent in the young and lean than in the old and obese, and in women rather than in men. So it's just a really interesting way that this uncoupling can be used for, helping us. Okay, that's actually this entire PowerPoint and the rest of this class. So this unit has been about gluconeogenesis and I'm sorry, not gluconeogenesis, gluconeogenesis. There we go. Excuse me, that was last unit. So this PowerPoint was primarily about, or I should say, this unit. Glycogenolysis, glycogenesis, and the pentose phosphate pathway. Then we talked about the tricarboxylic acid cycle, and then the electron transport chain. Yes, do you have a question? You can feel free to type it in the chat if you have a question, by the way. Yes, so I should say, so for the biochemistry review, we go from 10 to 11:15, that's Central Time. If you're here for, I believe there's a math review that happens right after, so if that's what you're here for, you've got plenty of time. Yes, we do record them, and I'll send you the link as soon as we finish this recording. Do you have any questions related to the content, or should I stop the recording here?